Hello everyone, this is Aarti Pandey from ThoughtWorks Technologies India, a global technology consultancy. Today I would like to walk you through our journey of scaling high volume, low latency, stateful stream processing application for a financial domain. The agenda is to quickly walk through problem statement and architecture, look at some infra and design considerations that we made, optimization and tuning done, and the insights that we received. Finally, we will keep some time for Q&A. Our problem statement was each incoming transaction had to go through a series of steps, including deduplication, fraud detection, and blocked card status check. The fraud detection operator was a tricky bit because it involved an external API call which had less than 10 milliseconds guaranteed latency. Blocked card check also was an external database call, and we had to optimize here as well. Our SLAs were 250K transactions per second as regular load, 1 million transactions per second as a peak load, and the end-to-end latency for every transaction had to be less than 100 milliseconds. Depending on the use case, we had to either use a file system as a source or Kafka as a source. It is very common in financial systems to have files as the mechanism of interaction between two systems still. However, from a futuristic perspective, we wanted to use a streaming engine which would either be able to read from a file or from Kafka. So we chose Flink. Back then, when we started in January 2020, the latest version was 1.9.1. Over a period of time, we also upgraded the Flink version and the Kafka versions for our application. Here we had three operators as we spoke about. First one was a stateful operator. The second one had an external API call. And the third one had to be expedited using an in-memory data grid, which is to check the blocked card status. Finally, the output would be returned to a sink, which will either be a file or a Kafka source. Now, keeping performance first design approach, we had to ensure that when we build the pipeline, we build it incrementally and we benchmark every single step or operator that we start adding to our pipeline. So the first question that we had was which source and sink would be better given this SLA or throughput. We wanted to know whether the file source like S3 would be faster or Kafka would be faster. A little experimentation revealed that more than the source, it is the nature of data that is more relevant for our scalability. For example, we need to have realistic quality and quantity of data. By realistic quality, what I mean is the message size should be realistic. If you have 1 KB messages or 5 KB messages or 10 KB messages, your throughput will depend on the size of your message. At the same time, you need to ensure that your data can be partitioned in a scale-out manner. If there are limitations, semantic limitations around partitioning of data, then that also affects the extent to which you can parallelize your pipeline. A bit of tuning is definitely something that helps in both the cases. In terms of sustainable peaks, you need to have sufficient inputs to be able to see the peak sustained for a longer time. And that's how you should be able to benchmark that. In our case, we could see that we could receive a high throughput on same hardware if we had sufficient input for a sustainable peak. Another critical requirement for our source operators was exactly one semantics. This being a financial application, accuracy was of utmost importance. For exactly one semantics, checkpoints are must. However, back then when we started in Jan, we figured out that Flink had a issue in terms of checkpointing with file source. Since the split enumerator finishes early and the split readers are still reading the data, one of the operators being in a finished state, the checkpoints simply abort and it doesn't work. Recently, as we upgraded to newer versions of Flink, we also saw that there was a watermarks generation issue wherein the file source after Flink version 1.10, the watermarks were not working. Because of these two reasons, we had to go ahead with Kafka source. And even with Kafka source, there were two different versions. The earlier version that we started with had some transaction related issues which kind of got fixed with a little bit of tuning and also some of the bugs that got fixed with 2.4.1. So having decided that we need a Kafka as a source, how big a Kafka cluster would be required was the next question. And at the same time, how big a Flink cluster will be required. What should be the number of brokers, partitions, and replicas on the source side, and what should be the number of transaction managers and the job parallelism on the Flink side. To understand how big a Kafka cluster is required, we first need to know our limits, because at this scale, your network could be a bottleneck or your disk could be a bottleneck, given that Kafka is a network and disk intensive system. Simple maths, if we have a 10 Gbps network line, and if we consider replication factor of 3, and considering that our message size is 1 kilobyte, at a cluster level, we will be able to publish 406k messages at a time, per second, right? Now, that's a simple basic without tuning, right? If you throw in a little bit of buffer memory configurations or message size configurations or compression configurations, that performance will be improved. Similarly, on the disk side, how much can every broker write per second? So for that, if the GP2 volumes that we used with AWS MSK Kafka had 250 MB per second write speed, with that speed, replication factor of 3 and the message size of 1024 bytes, a broker would be able to write 81k messages per second. Again, this is without any tuning. Throw in some buffer memory compression and message batching, this will be improved. But roughly, these are the limits that we need to watch out. On the consumer side, how much or how many transaction managers will be required? What should be the job parallelism? This really depends on two factors. One is the partitions that are there in Kafka, because your consumer cannot have more parallelism than the number of partitions in Kafka. And the number of partitions in Kafka itself depends on two factors. One is the extent to which your data that is in Kafka, that is published to Kafka, can be partitioned in a scale-out fashion, semantically without losing the meaning. Second, it also depends on what is your slowest consumer on the Flink side. Because in the Flink pipeline, let's say if Dedupe was the slowest one or the fraud detector was the slowest one, that's the maximum one consumer can consume from Kafka. And hence we need to work a little bit backwards by understanding the nature of our operator and then figuring out how many partitions or how many transaction managers would we need. So each operator here has to be benchmarked. If we start with the source and sink, and let's say we read data from Kafka and we write it back to Kafka using the Flink streaming engine. What we need to look at is this simple read and write operation, how much throughput can it give us? If I throw in more operators later on, that will definitely going to slow me down. But how fast can I read from Kafka and how fast can I write to Kafka? That is my basic limit for this particular pipeline. So to test that, we first put in the source and sink operator and then threw in the dedupe operator. Now our first operator was to check if this transaction is a duplicate or not. For that, it had to maintain some data for past few transactions, and that's why it was a stateful operator. In a while, we will see why it used the process element API. So it had to store the data for past few transactions, and the question was, where should it be stored? Should it be stored in the Flink's internal key value store, or should it be stored in some external key value store like Ignite or Redis? Quickly, the Flink's internal key value store would be local to a task manager, and hence it would be pretty fast. And it has an inbuilt lookup mechanism, and it is partitioned and distributed with corresponding stream partitions. Another important thing is if you had to, in terms of the recoverability from failures, if you have to recover your job after a failure, and if the state had to be rebalanced, Flink manages that efficiently internally. Whereas if you look at the external key value store like Redis or Ignite, even if it is installed on the same cluster, it will be slow because it needs an asynchronous IO call to it, and the throughput, as we observed, reduces generally by 30 to 40%. This also causes back pressure because typically the async operators are serial. So we decided to go ahead with the Flink key value store. Now, the way the key value store works is if you want to store some data, you have to choose some type of window. Now, session window was the most closest one for our requirement. If we again closely look at the requirement, for any given transaction, we wanted to go back in time for say 1 minute and check if this transaction was received in last 1 minute. If it was received, it is a duplicate. If it was not received in last 1 minute, then it is not a duplicate, which means for any given point in time, let's say at time t, we have an element, we need to look back from the timestamp of this element to t minus 1 minute and see whether it had a duplicate or not. Next moment at t plus 1, when a new transaction comes in, we need to look back from the timestamp of this element back up to 1 minute and see if there were any duplicates in this window or not. Same case for the next element that comes in, which means irrespective of how my time is progressing, the boundary of my window is actually defined by an incoming element. Every incoming element defines a boundary for 1 minute in the past. The second thing is the windowing is really in the past, not in the future. And as soon as an element comes in, we look at the past window and we evaluate whether this element whether this element is a duplicate or not, which means the element evaluation happens just at this point. Now, these three things is something that is not possible in the Flink session window. Alexander Zhukov has already written a blog around it sometime in July this year. While we started, we were experimenting with session window and we found that session window will not probably serve this. There were three reasons why the session window will not suit our requirement. One is the boundary of a given window is not defined by the incoming elements, whereas it is defined by particular time slots. For example, from T1 plus 1 minute, the window ends. T1 plus half minute, another window starts and it ends after that. So the boundary is not defined by the element. Second, when an element comes in, that it has to wait for the window to complete, and only when the window is completed, then the element will be evaluated. For an element that is received at this point, it has to wait until the window finishes at this point, and only then all the elements in that particular window will be evaluated, which means this operator will not emit anything till that happens. Remember, our latency guarantees were 100, or SLAs were 100 milliseconds, whereas our window is 1 minute. So we can't use this. The third thing is this windowing is in future, not in the past. For example, if this element is the current element, if I use session windows, I have to wait until this window finishes. I can't go back and look at the previous elements in this window because the window boundary is defined by time and not by the element. So given this, it was very clear that we had to implement our custom windowing. There is a possibility of using custom assigners and evictors. However, it's not very easy, and maybe it could also be tricky when you implement it using the windowing API. So we decided to go ahead with the process element API, which is the most basic or low-level API in Flink, and it also gives you a lot of control. Before we move into the details of how we implemented the custom window, if session window was to be used, there were three major drawbacks. One, because it was not in the session windows do not work in the past, so the accuracy of my deduplication will be affected because I won't be comparing it with the elements in the past. Instead, I'll be comparing them in the future. Second, latency. As we saw, the immediate evaluation doesn't happen. It has to wait until the window starts. And third, the window size itself. The window size basically means the amount of state or amount of data that operator will have to maintain for the period of window. In our case, the period of window was 1 minute and it had to slide with every incoming element. So every incoming element needs to look at 1 minute back, which means 1 millisecond slide. So 1 minute window with a 1 millisecond slide is huge. It's generally not recommended to go ahead with such a small slide for a large duration window. Let's say we assume that we had 50 task managers, a job parallelism of 50. And if our goal was to have 1 million transactions per second, each task manager will have to process 20K transactions per second. Now, let us look at what would be our window size if we have to process 20K transactions per second. Given window is of 1 minute, which means 60 seconds, multiplied by 20K transactions which are being received every second, it comes around 1.2 million transactions in a given window. Now 1.2 million transactions multiplied by the size of every element, which is, let's say, 1 kilobyte, makes it 1.2 GB of state. Now this 1.2 GB of state is for one single window. When we use session windows with 1 millisecond slide for 1 minute, it means that every window will overlap with 60,000 other windows. 60,000 windows because in 1 minute there are 60,000 milliseconds, and we are saying the slide duration is 1 millisecond. So that's why one size of one window, which is 1.2 GB, multiplied by 60,000 windows, which means 60,000 copies, because Flink internally creates one copy per window for every element. It comes out to be 72 TB state per transaction manager. This is huge. So even in terms of state optimization, going with session windows was not an option back then for us. And then we started looking at custom window. Here the calculation almost remains the same for the per window size, state size, which is 1.2 GB. What is different is because at every given point in time, we just have one single window which moves along as the new element comes in. And hence there will be only one single window for every transaction manager at any given point in time. Hence the state size would be 1.2 GB per transaction manager. Yeah, so this is some code. Quickly, since we want to move ahead, I'll just focus on the important aspects of this code, which is state pruning. We saw that the transaction manager size the state size per transaction manager was 1.2 GB, but that can be further reduced by ensuring that we do not keep entire transaction in the state, but we only keep those fields or attributes of an incoming transaction that are most relevant for deduplication. And with that, we could reduce the size of the element from 1 KB to 68 bytes, which is 93% reduction, which is almost like 81 MB per every transaction. We'll look at it shortly. Yeah. So 1.2 million transactions per window multiplied by 68 bytes is equal to 81 MB state per transaction, which is quite manageable now, right? The other challenge was if you're doing your own windowing, how do you clear the state? As I said, process element API comes with a timer API, a timer service, and you can register timers and clear those timers whenever you want. So clearing those timers for every element would be an overhead. That's why timer coalescing feature was something that was designed to optimize it. However, since we were using file state backend, which keeps most of the state in memory, in heap memory particularly, it has some impact on the garbage collection. As you see here, when we enable timer coalescing, the state is accumulated until the coalescence window. For example, if your coalescence window is half a second, till half second, which means that 30 milliseconds, for 30 milliseconds, the data will be accumulated and it will be cleared only after that. This means the heap size grows on and there is a little overhead on the garbage collection side also. That's the reason when you with file system state, if you turn on the timer coalescing, your heap state management, garbage collection gets affected. Without the timer instead, you can see that the state is being cleared very often. It has a little overhead on the CPU time. However, the memory access pattern is quite uniform and sustainable, whereas if you see it here, it's not quite sustainable. Further optimizations we tried in terms of serialization, which means the kind of data types that we use for our transaction and the fields inside it. We preferred tuples over anything else because tuple serializer is the fastest one. Then state backend tuning. We know that we have RocksDB and file system as two options. However, as we know, RocksDB requires serialization for every state access, and hence it was slow. But we wanted to know how much is it slow. So when we experimented with file system and RocksDB backend, we found that even after tuning the memory model has been changed after Flink 1.11. However, even after tuning the memory required for file system as well as RocksDB, the throughput difference was up to 30%, which means file system backend gave 30% more, 30 to 40% more throughput than RocksDB backend. Since our SLA of high throughput was something that was important, we went ahead with file system backend. Another tuning that is required for stateful operators is checkpoints. For exactly one semantics, checkpoints are absolutely necessary. While asynchronous checkpoints are possible with both file system and RocksDB state, we also had to ensure that there is a minimum delay between two checkpoints. And at any given point in time, there is only one concurrent checkpoint going on. Another feature that came in handy with the file system backend was snapshot compression. Although it is using Snappy right now and we don't have something like LZ4, but snapshot compression also helped reduce the state size per transaction manager. Yeah. So given all these, after doing all these optimizations, what was the throughput that we got for dedupe operator, which was the only stateful operator in our pipeline? As you can see here in the screenshot, about 1.8 billion messages processed in 529 seconds, which is around 3.5 million transactions per second, and there was no back pressure. So this was almost, or this was slightly higher than what we wanted. But remember, we have two more operators to come in, and that's why a higher side throughput on this operator was essentially required to maintain the throughput for the entire pipeline. Quickly with this run, if you look at the checkpoints, the average size of checkpoints, or the duration that the checkpoints was around 3 seconds. The checkpointed data size was 1.2 MB or 1.1 MB, something like that. And most of the time in checkpoints was spent in alignment and not in saving, which happens asynchronously. So majority of the time was in alignment, which is fine because unaligned checkpoints is a beta version feature right now, experimental one, so we didn't go for it. Our second operator was fraud detection, which had to do an external API call, as we talked about. For that, we chose async IO operator. However, async IO operator is a serial one. On top of it, we had to use ordered wait because we had to ensure that the order of transactions is preserved. So with ordered wait, it becomes even slower. The performance impact was around 80 to 90% throughput reduction compared to the dedupe operator. The dedupe, which was upstream operator, also had a lot of back pressure, and there was a lot of effort involved in tuning for reducing that back pressure. Async IO, given it is a multi-threaded operator, CPU started becoming a bottleneck on 4-core machines. So we had to go for 8-core machines. Even on 8-core machines, as we started tuning for back pressure, increasing the parallelism level of the operator, CPU usage started becoming high. Tuning on the async IO operator or the async HTTP client had very less impact, no significant impact. We tried tuning the buffer capacity, the timeout, number of connections per open, keep alive, parallelism of the operator itself, but it had a very, very little impact on it. In general, it is tricky to have an API call in a streaming application, and especially on limited core machines, it becomes trickier. One subtle thing to watch out for in case of fraud detector is the optional executor argument that is there in the future API. Because it's an optional argument, you may forget to put in an executor there. And if you don't put in an executor there, by default, the fork join pool is used. And this may not be a problem for streams that have very less velocity of incoming elements, but with high velocity streams where incoming elements are coming at a rate of millions per second, the fork join thread pool, in order to keep up with with those many elements, the fork join thread pool starts work stealing, and the work stealing count increases almost up to the number of elements that are being processed, resulting in millions of new short-lived threads being created for every element, and that slows down your JVM. That also affects the performance. The general guideline is to use direct executor. However, we need to look at whether the direct executor gives more throughput, or a slightly medium approach where a fixed thread pool with, let's say, number of cores divided by 2 as thread size would give you more improvement. Well, the throughput increases with slightly higher number of threads, which is number of cores by 2. However, the latency also increases by 50%. So you'll have to seek that balance between latency and throughput when it comes to the thread pool size. But it's important to remember, because this is an optional argument, and if you miss it, the fork join thread pool really affects the performance a lot. The other thing that we tried was stream splitting, because the async IO operator was the slowest one. We thought that if we invoke it over a split stream and let the rest of the pipeline continue on the main stream, we would be able to at least do 2 things in parallel, and that would improve the end-to-end latency for a given record. However, the hypothesis was proven wrong, and we could see that the number of elements that the pipeline has to process doubled, because side output, the number of elements in side output was exactly equal to the number of elements in mainstream. And ultimately, we had to join both the side output and mainstream, because the output had to be from both the streams. And that kind of resulted in wait in that join operator. So it didn't help us. The last operator in our pipeline was to check the blocked status for a given card on the current transaction. And instead of doing a database call, we thought of using an in-memory data grid, which would be a faster IO or faster read operation. Here, we also tried to use distributed cache before going for an in-memory data grid. So Flink's inbuilt distributed cache would keep 1 copy of that data on every task manager. Given that we were using file system state backend, which already uses heap, and even the distributed cache would use heap, given the data size, since it was very large, we did not go for distributed cache. We did not want those many copies per transaction manager or per node. That's where we thought of using an in-memory data grid. Fortunately, we found out that the in-memory data grid latency was 2 to 3 milliseconds. And with that, we assumed that if we use a rich map function with a simple map operator, it would read from the IMDb in 2 to 3 milliseconds, and we would be good with that. However, our throughput dropped by 50%, and the per element latency, which was earlier 2 to 3 milliseconds, in the pipeline, the latency became 2 to 10 milliseconds for that particular operator. And then we realized that the fastest operation, which is a IMDb read with 2-3 milliseconds, was giving lesser throughput than an external call, which was taking a 10 millisecond latency. Now, the reason for that was that the map function is a synchronous function. So at any given point in time, it will serially invoke the IMDb read call for only one operator at a time. And once that call returns, then it will send out another call, which means here the synchronous nature of the IMDb read slowed us down. Switching to an async IO operator to read the IMDb addressed the slowness in the sense that the throughput was back to the upstream operator's throughput. Even the back pressure on the upstream operator got solved. Little bit tuning on the parallelism of this particular IMDb operator address the back pressure on the upstream operator. This was a classic example and learning for us that even if you have a 2-3 milliseconds call, you should not use a synchronous call when you cross a system boundary from going out of the JVM. Yeah, so with that, let us come back and let us look at the micro benchmarks that we did. As I said in the beginning, with the performance first approach, when we started designing this pipeline, for every operator, we tried to get some benchmarks from the cluster that we had. So for the first operators, which is source and sink, just reading from a source and putting it into a sink, we got a throughput of around 6 million transactions per second. Simple read and write. Adding the dedupe operator, the throughput reduced to 3.5 million transactions per second, as we already saw in the screenshot. Adding the fraud detection operator further reduced the throughput by almost 80%. And as I said, this was mainly because async IO operator is a serial one. Multi-threaded operator has some CPU impact, and there is also latency involved in receiving the response for a given transaction. Typically, we should avoid external calls. Yeah, and the last operator, which was blocked card check operator, actually because it was slowed down because of the fraud detection or because of the upstream operator which had an API call, the blocked card check operator per se did not have additional impact on the throughput or latency. So the takeaways for us from this exercise was that stateful operators were the fastest one if you tune it properly. API call was the slowest one, and we should avoid API calls, especially at this scale. Instead of reading a database, IMD, the in-memory data grid read definitely helped us. With that, one another thing is, while the throughput of the entire pipeline end-to-end with all operators was reduced because of these slower operators, if we take out the processing from each element, and if we just keep each element as a no-op element which doesn't do anything but just takes the data and puts it into the output. But if we maintain the parallelism level as it was in the pipeline, with the same parallelism level, because there is a hashing or rebalancing involved when you execute it on a larger cluster, just to understand what is the latency introduced by the topology compared to a source and sink operator, we tried this, wherein the parallelism level was same, and we saw that the throughput was 4.8 million, which means compared to a source to sink throughput, which was 6 million, if we add in these operators, and these operators would not do anything, just take the incoming data element and push it forward. Even with that, because of the hashing, rebalancing, and shuffle that has to happen, the throughput was down from 6 million to 4.8 million. This was a good insight because we now know how much maximum throughput to expect from our pipeline. Yeah, quickly with pipelines and slot sharing, adding more slot sharing groups didn't help anymore. Splitting resource heavy operators into different slots actually degraded the performance because the distribution of tasks was not even. One full job instance per transaction manager was definitely helpful. And backpressure tuning actually needs to be done on the real size machine that you will be using in production. Any other backpressure tuning that you do on any other machine would not be helpful. Also, the benchmarks that you do need to be done on the final size of your cluster with final type of machine that you will be using, because backpressure is something that you would be optimizing at every time because it varies with just every single small change. With that, we come to questions. Thank you.